Okay. So we're thinking about what do weak acids react with water to form. So I like to write every weak acid as an HA. Okay, monoprotic weak acid, HA. If we allow it to react with water and have an equilibrium, it's going to form H3O plus and A minus. Okay. Oftentimes we'll see weak bases written as B, I guess for base. They react with water to form a protonated species, BH plus for instance, and hydroxide. So note the difference. A weak acid reacts with water to form acid, H3O plus. A weak base reacts with water to form base, OH minus. Okay. But again, equilibrium arrows, ionization does not occur completely. And so when we want to calculate equilibrium concentrations, we get to use ice tables. And that is where we will start next time. Have a good day, everyone. Yeah.
Let's do like cyclics. So like if a problem like asks you to so basically for calculating the pH, are you like supposed to like round it and then each afterwards? So like because there's a difference between like so this is me calculating pH. And if I use the rounded number, it gives you a different decimal. Like versus if you were to use the actual data.
Yeah, you're right.
Yeah, it's one of the homework problems. It's just not, I didn't want it to be second after that. So.
Oh,
But it's
I
okay.
would probably round at the end, so using that
That one.
yeah.
Gotcha. Okay.
Yep.
Thank you.
Good luck. Okay.
What's due here?
Okay.
I thought it was like 10 to the negative log.
It is. Yeah.
But whenever I plug it in, I always get like some big numbers, like really
Okay.
large numbers.
Let's try it.
Of course, I can literally.
Have a good day. See you. Oh, it's not minus the log. It is 10 to the minus pH.
Oh.
Here, let me go back to that slide. So here we are. So let's start now thinking more about this weak acid equilibria. HF is a weak acid. It has a Ka associated with it. The acid dissociation constant for HF is 6.8 times 10 to the minus 4, which is relatively large, meaning that there is a good amount of conjugate base formed. The reason I know that's relatively large is just from experience with a bunch of different weak acids. That's on the large end of the scale. So if we write our acid ionization constant, or Ka, for this equilibrium, we'll have Ka equals the concentration of F minus times H3O plus divided by HF, concentration of HF. Again, water is a pure liquid, so we don't include it in the equilibrium. And then that is, of course, equal to the constant, 6.8 times 10 to the minus 4. So just like we did with our equilibria chapter, we're going to be able to write equilibrium constants for our acids. The A is specifically saying this is for a weak acid. And one of the things that I like to do when I'm working with weak acid equilibria is no matter what the weak acid is, if it's monoprotic, I say that its formula is HA. HA just is standing for weak acid. And the reason I do that is it makes every weak acid problem look nearly identical. Okay? Every monoprotic weak acid problem is now HA in equilibrium with water, A minus, and H3O plus. And so the only real variables are now the numbers that we're going to plug into an ICE table or Ka and things like that. Okay? You'll see we're going to do an example of acetic acid. We're going to look at an example with acetyl salicylic acid. Both of those we can easily abbreviate HA. Okay? I do it for simplicity. And I also don't have to write out giant formulas. So simplicity and laziness is what drives everything. Okay, so if we use a weak acid equilibria that our general equilibrium, so we're going to have HA plus H2O in equilibrium with A minus, that's the conjugate base, and H3O plus. And now our Ka is going to be equal to the concentration of A minus times H3O plus over the concentration, of HA, sorry. Looking at the one above. Make sense? I think maybe your book may use HX instead of HA. Keep an eye out for that. Maybe the homework, I think that shows up occasionally. All the same thing. H plus instead of H0 plus. Yes, so we could do HA in equilibrium with A minus plus H plus. Yeah. Same thing. Okay, other questions? Okay. So again, don't really know what I was thinking in putting this slide here, but here's a list of weak acids and their Ka values. The question here that is posed is which acid has the greatest quantity of conjugate base in solution? So the acid with the greatest Ka value is going to have the greatest amount of conjugate base in solution. Larger the Ka, the more products are formed. Okay? So which one has the smallest quantity is the one with the smallest value of Ka. In this case, that's phenol at 1.3 times 10 to the minus 10. Okay? So very little conjugate base is formed from phenol. Okay. We can also write our weak base equilibria and have a weak base constant associated with that. That's our base ionization constant, Kb. And for this base, NH2CONH2, I think this is urea. I never remember. This will react with water to form the conjugate acid and OH minus, the base. Now you'll notice this is a lot to write out, and again, I like simplifying things. So we can say for a base, B plus water in equilibrium with the conjugate acid, BH plus OH minus. So again, remember that a base is going to accept a proton. So we go from a base B, we're pretending that's our generic formula. We add a proton H plus to that, it's going to form BH plus. Okay, the positive charge comes from the fact that the proton has the positive charge. Okay. And so we can write a general KB. KB is equal to BH plus, concentration of BH plus times the concentration of OH minus divided by the concentration of B. And again, just simplify every weak base problem by doing that. Okay. That make sense? Okay, so let's actually do a calculation concerning a weak acid. So here we have a 0.1 molar solution of acetic acid, and it has a Ka value of 1.7 times 10 to the minus 5. And we want to determine the concentration of conjugate base in equilibrium, when it's at equilibrium for this solution. And while we're at it, we can also calculate the pH. That's going to be something that you frequently encounter. Okay? So this 0.1 molar solution of acetic acid, that concentration of acetic acid is the initial concentration of acetic acid. That does not account for what exists of acetic acid at equilibrium. When we put this acetic acid into water, some of it's going to dissociate from the conjugate base, which is acetate ion, and some of it's going to stay protonated, stay as acetic acid. Okay? But this 0.1 molar is only what we start with. So that's an initial concentration. So we're going to have 0.1 molar for our initial concentration of acetic acid. Not going to worry about water, it's a liquid. And initially we have 0 moles per liter of acetate ion and 0 moles per liter of H3O+. So looking at the way this reaction has to proceed in order to reach equilibrium, we only have reactant, and so we need the reactant to form product in order to reach equilibrium, which means some amount X of the acetic acid is going to react to form acetate ion and H3O+. Everything has a stoichiometric coefficient of 1, so it's minus 1x for the acetic acid, plus 1 for acetate ion and H3O+. So then at equilibrium, we're going to have 0.10 minus x for our acetic acid, x moles per liter of acetate, and x moles per liter of H3O+. Everyone okay up to here? Okay. So if we want to solve for the concentration of conjugate base, we need to solve for x. We can use our acid ionization constant, or Ka, equal to 1.7 times 10 to the minus 5. Again, this is equal to the concentration of the products, multiplied together, divided by the concentration of the reactant. So to simplify that, we have x squared divided by 0.10 minus x. Everyone okay there? Okay. How do we solve this problem? Yeah.
You should just be able to get rid of the x in the denominator, right?
Why is that? There is a reason.
It's because it's such a low concentration.
Yeah. Who are you going to say? If it's smaller than 5% of the initial concentration, you can ignore it. Okay, that's a reasonable one. That's what the book says? Great. I use a different definition, but if that's what the book says, let's write it down. If what is 5% of, oh, but then you have to calculate it to find out, right? Yeah. Here's another rule. That's why I don't usually use that one. Okay, so what we're saying is, if you solve this equation this way, you have to use the quadratic formula, which is, well, yeah, you can use your TI whatevers, right? So you have that all programmed in there. Is that what the thing? I don't know. No, I don't know. That was the one thing I used my calculator for 20 years ago or 30 years ago, whatever it was. TI whatevers, yeah. Okay, so you could solve the quadratic, or you can make an assumption. And then you don't have to use the quadratic, which is my preferred method. If the initial concentration of HA, so HA sub 0, 0 is for initial, divided by the value of Ka is greater than 1,000, then you can ignore x in the denominator. And that's because when you subtract a really small number from 0.10, it doesn't make any difference mathematically, right? It's going to come out in terms of significant figures. So if we have our initial concentration is 0.10 and our Ka is 1.7 times 10 to the minus 5. I didn't do the math, but that is greater than 1,000. Okay. The other thing you can do is look at the difference in the powers. So we have 1 times 10 to the minus 1 and 1 times 10 to the minus 5, and there's a difference greater than 1,000 there. Yeah. So that's another way of doing that if you don't want to actually do the math. Okay. So let's say, okay, we can assume now, we've done this calculation, we know that the value of x, assume that x is much smaller than 0.010. So then we get 1.7 times 10 to the minus 5 is equal to x squared divided by 0.10. And that's a much easier equation to solve, right? Okay. So if we do that, we find that x is equal to 1.3 times 10 to the minus 3. And that's our concentration in moles per liter. And this, of course, then is equal to the concentration of the conjugate base, right? X is our conjugate base at equilibrium, acetate ion. And it's also equal to our H3O plus concentration. Everyone okay with that? Yes. Okay. So I guess with this 5% rule that your textbook uses, if you do this calculation and 1.3 times 10 to the minus 3 is greater than 5% of 0.1, then you have to go back and do the quadratic. So it's kind of ends up being the same. I guess I like knowing ahead of time that I'm not going to have to do the math twice. The other thing to keep in mind, so if you solve the quadratic versus if you make the assumption, right, the difference in the answers is going to be really small. So let's say you're taking a multiple choice exam, right, and you're looking at the answers, and I guess there could be a fill-in, like a formula question, right, so this is sort of not the same, but if you have a multiple choice question, you look at the answers and the answers are not very close together, it means that you probably don't need to solve the quadratic. You know what I mean? Right? So if their answers were possible like 2.89 and 2.85, okay, then there's something there, okay? Otherwise, they're not going to solve the quadratic. Because the difference in what you calculate with the quadratic and without the quadratic is going to be a very small concentration. Does that make sense? Okay, so we know that this is our H3O plus concentration. We can easily find the pH. pH equals minus the log of 1.3 times 10 to the minus 3. And what do we get here? I guess I didn't do it because I wasn't in the problem. 2.89? I guess, just say that. Oh, yeah. I must have done it. Oh, no, it's right there. Okay, got it. Okay, good. I'm not just seeing numbers. Is in my notes. God. Okay. Any questions on that? There is another calculation that's important for you to understand, and that is percent ionization. So percent ionization simply refers to the amount of conjugate base that's formed from a weak acid dissociation or from a base ionization. So percent ionization is the amount of species that is ionized divided by the initial concentration times 100 to get that percent. So it's initial concentration of acid in the denominator, equilibrium concentration of conjugate base in the numerator. Okay. So what this is saying is how much of our initial concentration of acid has ionized to form conjugate base. Okay. Your book uses a slightly different formula for this. Works out to be the same thing for the most part. There are a couple of exceptions. But I'll write it here as well. Percent ionization, I'll just do percent I. What your book uses is concentration of H3O plus divided by the concentration of HA initial times 100. So we saw in the last problem that the concentration of conjugate base and H3O plus are equivalent at equilibrium, right? For every one weak acid that forms conjugate base, there's one H3O plus that's formed. So essentially, these are equivalent expressions. So be comfortable with both of those. Does that make sense? Yeah.
So will this only work if we're looking at a weak acid? Like,
You could do a weak base. So for the base, it would be concentration of BH plus over the initial concentration of base times 100. Or, following what the book does, concentration of OH minus over the initial concentration of base times 100. Yep. Good question. So it's the amount ionized over the initial. So for our acetic acid problem that we just did, where we formed 1.3 times 10 to the minus 3 molar acetate ion, we initially started with 0.1 moles per liter of acetic acid. Our percent ionization then is the 1.3 times 10 to the minus 3 divided by 0.1 times 100 to get 1.3%. Okay? Reasonable? So a very small amount of acetate ion is formed from acetic acid. Here's another problem. This is a nice comparison. We have a larger Ka value here, 3.3 times 10 to the minus 4. We were at 1.7 times 10 to the minus 5, okay, for our acetic acid. Keep that in the back of your mind. Here we have a 0.10 moles of acetic acid, acetylsalicylic acid dissolved in 0.54 liters of water at 25 degrees Celsius, what is the pH of the solution. So again, watch this because we're not using a 1 liter vessel. You're given moles and you're given a volume. We need to use concentration in our ice table. Okay? We can write out the equilibrium expression for our weak acid, acetylsalicylic acid, HA. Put that in water, and in equilibrium we're going to have H3O plus and A minus. Okay, doesn't matter what the formula is for acetylsalicylic acid. We have 1 Ka, so we know it's monoprotic. If it was diprotic, it would have 2 Kas. So we need an initial concentration of HA. We were given moles. We have 0.10 moles. And we have 0.5400 liters. And so we end up, I missed a 0? Oh, yes, I did. There we go. Okay, so we end up with 0.00360 moles per liter for our initial concentration. Why don't you take maybe 2 minutes, work through what you can to solve for the pH of the solution, and we'll do percent ionization in a bit.
How do you increase percent ice?
How do you increase it?
Yeah, and since like liquid has like a lot of ions, so it's hard. So
The Ka value will make it higher. That's not something you can affect. Yes. Is it not?
I got 0.033.
Did you do, hang on. Oh, yeah. Hey, y'all, I made a mistake. Hey guys, just want to correct this for you. We get what are we getting? 0.33 moles per liter. Yeah, who knows what I was doing? 0.0, oh, because I made that mistake in my notes that I had 0.18, that's why. Okay, so yeah, we should have 0.033 moles per liter for our initial concentration. So the other thing that affects percent ionization is that initial concentration.
so if it's higher.
No, I think it's weird. I can't remember what I'm thinking about.
So like in this section problem, we actually have to do the quadratic formula.
I gotta rework it now. All right. So hopefully you corrected for my mistake there in my math. See what I did in my notes. What I started about. So at equilibrium, we're going to have 0.0333 minus X moles per liter of our acetylsalicylic acid. We're going to have X moles per liter of the conjugate base and X moles per liter of H3O plus. If we write our acid ionization constant, 3.3 times 10 to the minus 4, set it equal to X squared over 0.0333 minus X. And we can check and find that we actually do have to use the quadratic formula in this case. Now, because I have a mistake in my notes, I don't have it all written out. So has anyone solved the quadratic? Braden, got my back.
3.16
For X. Okay. Okay, so using the quadratic, let me write out the, in case we don't remember, because it's, certainly been a while for me. When we're using the quadratic, we write it in the form ax squared plus bx plus c equals 0, and we can solve for x. X equals minus b plus or minus the square root of b squared minus 4ac over 2a. Remember all this? So when you're writing out this equation, we're going to have 1.11 times 10 to the minus 5 minus 3.3 times 10 to the minus 4x minus x squared equals 0. Whoa. When you're writing it out, yeah, did I do something wrong? What's your question?
You explained again how you knew that you had to.
I didn't write that down. Okay, so how do we know we have to use the quadratic? If we look at our initial concentration of HA divided by, doing it backwards. Oh, yes I am. Divided by the Ka, this is 0.0333 divided by 3.3 times 10 to the minus 4, and that's equal to about 100, which is less than 1,000. So we know we have to do the quadratic. Just can't read that. When you do these quadratics, you should end up with two coefficients that have minus or negative signs and one that's a positive. If you don't, you've done something wrong. Yeah?
Can you show how you got the
1.1 times 10 to the minus 5 is the 0.0333 times 3.3 times 10 to the minus 4. Is it good?
What was that x for?
And x is this. Let's do a quick little thing here. What if we hadn't used the quadratic? I haven't tried this, so this is an experiment for me too. Let's say you forgot to use the quadratic. You get this expression for Ka, right? And so you say that x is small in comparison to 0.0333. So we're gonna have 3.3 times 10 to the minus 4 is equal to x squared over 0.0333, okay? And we solve for x. In doing so, I get 3.33 times 10 to the minus 3 molar. Okay. So the difference here, when we use the quadratic, we get 3.16 times 10 to the minus 3. When we don't, we get 3.33 times 10 to the minus 3. We get a pH of 2.47 for this. 0.016 and 2.50 for this one. So the correct answer is a pH of 2.50. So you can see they're fairly close, right? Yeah.
In this case, we have like the two x values. You get one positive and one negative.
Yes.
But if there were two positives, how do we know which one to use?
I think if you get two positives, you've probably done it incorrectly.
Okay.
Yeah. Additionally, you would, the other way to do it, in case that happens, because I think I've seen it happen like one time, you would subtract whatever x you get from your initial concentration, and as long as you get I think one would have to give you a negative in order, and then you would know it was wrong. Yeah.
So like on the exam, should we just do it without the quadratic if it requires a quadratic?
Yeah, so the question is on the exam, do you do it without the quadratic and hope it's good? I mean, speaking about, you have a limited amount of time to take your exam, that's probably the approach I would take. If it's a fill-in, like when we have to punch in the actual answer, I might be a little bit more cautious and maybe check the assumption. The initial concentration of HA over Ka, check that first. But otherwise, I would just solve it, and there is no way we could do those two answers and say pick the right one, because that would just be rude. Okay, maybe we will do it.
Not you got to try, but.
Other questions? So the other thing that you might want to recognize is that in order to save yourself some time, for every monoprotic weak acid, you're going to end up with a Ka equal to x squared over that initial concentration of HA minus x. It works out the same way every time. And that could be a useful tool. I don't know if I've memorized the equation, but just recognize that that's where you're going to end up. So. All right, other thoughts, concerns? Oh, that's the end of that slide. Okay.